Hey homies, and welcome to Dilations, a part of the methods 3 and 4 here in Australia, but also very useful around the world. Little series of videos I'm doing. Welcome to my channel if you are new. It's lovely having you here. Now, I have to say, I see the word dilation and I shudder a little bit because I just think of childbirth, and that's a whole video that I'm not getting into at any point. Thank you very much. No, we're going to deal with the mathematical dilation. But before I do that, if you are new or you have just stumbled across this and wouldn't mind doing so, could you subscribe? There's an arrow over there that says something along the lines of, let me know you're watching. That's a little trick for me for subscribe. Subscribers make all the difference. It sort of helps me know that I'm doing something useful. I am a very small person trying to do a very big job, and that's cover all of the maths syllabuses for all of Australia and other parts of the world. So thank you very much for anything you can do to sort of help me out there by subscribing and telling your friends to subscribe. But as is normal, let's have a look at what I want to know by the end of this lesson. Well, obviously, know how to dilate something. It's the whole point of the lesson. Know how to use correct notation, sketch these things, transform these things, and know how to use algebra. Now, this is a continuation of a previous video. So if you haven't watched the one before on translations, please go back. There is a link appearing above me here or here. I don't know which side of the screen I'm on. That hopefully you can follow and have a look. Now, as I say here, we looked at the previous lesson at how we can translate either an individual ordered pair or a set of ordered pairs, otherwise known as a function or a relation, using algebra or a shortcut. Now, translations, as I say here, form just one part of a set of what we call transformations. And the methods 3 and 4 book, 2/3 of it deals with absolutely everything to do with transformations. If you can't do this chapter and you can't apply it or understand it or do the algebra or even just move them around, draw them, visualize them in your head, sadly, I think you're going to find the work very, very challenging, and I don't want to put you off. So just sit here and just keep having a go at this particular work and these first few chapters of the textbook, and I promise you it will pay dividends. So what is a dilation? And I say here I love a good dictionary definition. So what I did was look it up on dictionary.com, and it says the action or condition of becoming or being made wider, larger, or more open, which is physiology. Random, because it's also mathematicallyology. The action of speaking or writing at length on a subject. Yeah, okay, that's too much information. Long story short for mathematics, and that was very loud. Sorry if you thought I shouted at you there. Dilation is basically a stretching. All right, so just to go back to pregnancy, dilation is a stretching. Enough said. Thank you very much. Maths. Now, we can stretch away from the x-axis, and you'll notice whenever I do this, or if I teach this, I actually always do hand actions, random. But we dilate away from the x-axis or away from the y-axis. Now, a dilation can happen in two ways. We can squidge it closer to the y-axis, or we can squidge it, squidge, good word, further away from the y-axis. Alternatively, squidge it closer to the x-axis, or squidge it away from the x-axis. Now, what happens as a result is really, really important. So if we consider the following unit circle, we have here the equation x squared plus y squared equals 9. And if we remember anything, the equation of a circle is given by x squared plus y squared equals r squared. Hence, the circle on the left has a center of the origin. Now, the way we know that it has a center of the origin is because this equation here, if it's just x squared and y squared, has a center of the origin with a radius of 3. And we know it has a radius of 3 because r squared is 9. So r must be 3, or minus 3, but it can't be minus 3 because you cannot have a negative radius. Now, what I'm going to do first is look at what happens when we dilate away from the y-axis. So we're stretching this way. Now, when you're stretching this way, which actual coordinates are changing? Well, hopefully you'll realize it's the x coordinates which are changing as a result of that dilation. So with this original function here, we have x squared plus y squared equals 9. So that's my original function, the one I used earlier. And what I've done here is I've come up with two dilations. What you'll notice is because I'm stretching away from the y-axis, then we notice that actually it's the x values or the x part of that equation which is changing. Now, going back to when we did translations, do you remember that when we had y was equal to x minus 1 squared, this value here did not move it to the left, did it? It actually moved it to the right. Sorry, I have a fly in my studio now, and I'm a little bit concerned it's going to pick up on the audio. Mr. Fly, please go away. So the same principle is very, very true here in dilations. When it's inside that bracket, it's doing the opposite of what you're actually expecting it to do. So if we look at the blue function, we've replaced x with x on 2. We seem to have halved my x values. But when we look at the graph, what was -3 has now become -6. So we haven't actually halved those values, we have doubled them. Congratulations. And likewise here, when I've doubled my x value inside that bracket, what has happened? Well, it hasn't actually made it twice as big, it's made it half as big. And I suppose, again, it comes back to this idea that when it's inside that function, it's doing the opposite of what you're expecting it to do. So if we now look and sort of confirm our thinking or our understanding here, what I'm now doing is I'm dilating away from the x-axis. When we dilate away from the x-axis, it's our y values that change. Notice how the graph is getting taller. So again, here's my original function. The red one's my original function. My blue one now, I've replaced y with y on 2. So I'm saying let's halve all my y values, or my y values we think have been halved, but actually they haven't. Once again, that was 3, that's become 6, and so it's doubled. And likewise, when I look at the green one, which seems to have the circle squidged in, I love that word, squidged, what looks like in the brackets that we've doubled, in fact we haven't. So what was 3, in fact, becomes 1.5. So this is really, really useful to know. But as I've done previously, using algebra can sometimes, for more complicated questions, make our life a lot easier. So we know that a coordinate has its image and pre-image. Now again, the pre-image is effectively the original coordinate-ish. So let's call x, y my original coordinate, and let's say x dash y dash is my image. It's what's happened after my transformation. When we dilate away from the x-axis, so like we say here, we've dilated a factor 2 away from the x-axis, it means we're doubling all of our y values. Now I know that sounds counter to what I've just said, but we're trying to look at sort of things from the beginning now. So all those 4 graphs I've done, just put them to one side at the moment. Actually, I only did 2 graphs. I did 4 graphs in the previous video. Anyway, losing the plot. Just look at what happens now. So if we've got an original coordinate x, y, and it's going to have a dilation away from the x-axis, we now know that the y value is going to double. This is the transformation algebra, remember. When we dilate from the y-axis, we know the x values are going to change. So if we dilate from a factor of 2 away from the y-axis, then my x value doubles. So let's have a look at an example of an ordered pair. So if I had 2, -3, and I do factor 2, we do a dilation, factor 2 from the x-axis, then what that means is that, if you remember, my y values are going to change because I'm stretching the graph this way, so my y values are changed. And they're going to change by a factor of 2. So my original point was x, y. So that's going to become x, 2y. So I'm going to double my value, and as such, that stays the same, and that becomes -6. If I have the same point 2, -3, and now we'll do a factor of 3 from the y-axis, then what I'm now going to do is say, well, what was originally x, y, I'm going from the y-axis, so that my x values are changing. They're becoming 3 times bigger in that situation, and so that would make that 6, -3. Now, obviously, we can't do that for every single coordinate on a function, so we need to be able to find a way of doing this using sort of function notation and algebra. Okay, so we have the equation of a circle with center, origin, and radius 4. So first things first, x squared plus y squared is equal to 16. That's the equation of my circle, center, origin, radius 4, which is now being subjected to a dilation from the x-axis of 2 units. So from the x-axis, 2 units. So I'm stretching that way, factor 2. So I'm going to do an arrow and a times 2, and a dilation from the y-axis times 3. So it's that way times 3. Now, the great thing about this algebra stuff is you can actually do it all in one. You can do it one at a time, or you can do it all at the same time. So I now know I'm going to say, well, if I imagine I've got my first point, which was x, y, and I'm going to do my stretch of 2 from that way, my y values are going to double. So that's going to become x to 2y. So that's the first part. The next one is 3 that way. So that now means I'm stretching 3 that way, which is my x values are changing. So that becomes 3x, 2y. Why is this important to me? Well, because I now know this new point there is the image, otherwise known as x dashed and y dashed. How is that helpful to me? Well, now like I did in the previous video, is I compare, I equate those. So I know that 3x is equal to x dashed, and I know that 2y is equal to y dashed. But why is this important to me? Too many y's in this example. Well, my original equation is x squared plus y squared equals 16. I want to have this in terms of an x dashed and y dashed. I want to get rid of that x and y. So I'm going to rearrange this to say that x becomes equal to x dashed on 3. And y becomes equal to y dashed on 2. And again, ask yourself the question, whenever you get to these questions, say, well, why am I doing this? Other than you have to, because it's part of the course. Right, so I want to replace that x with an x dash. That means I've got to have equations equal to x and y. I've got those. So that now becomes x dashed on 3 all squared plus y dashed on 2 all squared is equal to 16. And as I said in my previous video, once we've got those points in there, I don't need the dash anymore because it's the equation of my new function. And so x on 3 all squared plus y on 2 all squared is equal to 16. Now you may at this point want to multiply that out and have it as x squared over 9 plus y squared over 16 equals 16. Over 4 equals 16. But my advice to you is don't. It actually makes life a lot easier when we have functions we can directly compare to the original and see automatically what our transformations were. So again, because we were stretching 2 units from the x-axis, that's why we have a half in the y and vice versa. Now, again, there are always shortcuts. Dilation from the x-axis, factor b. So again, just putting a letter here so that we can sort of formalize this. When we have a dilation from the x-axis, factor b, we replace the y with y on b. All right, so again, because the x-axis changes the y, we replace it with y on b. Likewise, when we have a dilation from the y-axis, then we're changing the x values, and we replace x with x on a. So for the function f of x is equal to x minus 3 all squared plus 4, find the equation of the transform function if f of x has been subjected to a dilation from the x-axis factor 2, so it's that way times 2, and that way times 4. All right, so the theory states that I want to replace x with x on a. And what is the value of a? Well, a is the y. So what am I doing away from the y-axis? 4. So I'm going to replace x with x on 4, and I'm going to replace y with the movement away from the x-axis, the dilation away from the x-axis, which was 2, so y on 2. So knowing that, and get rid of that now so that I can do this, I have my new function as f of x is equal to, where I see an x, replace it with x on, in which case let's put that 4 there, just so I remember, x on 4, minus 3 all squared, plus, and where I see a y, y on 2. Well, I don't have a y, but I have a function of x, so that now becomes y on 2. I could have written f of x again. So much notation. So we now know that y is equal to multiply everything through by 2 lots of x on 4 minus 3 all squared plus 8. And ladies and gentlemen, that function there will be this original function which has been subjected to a dilation 2 that way and 4 that way. Now it's really important to be able to do things backwards, and I'm going to do one example here before I get on to sort of later exercises that will hopefully show you how to do things backwards. And the example says, determine a factor of dilations when the graph of y equals the square root of 4x is obtained from the graph. So this was my original graph, and this here is my new graph, y equals the root of 4x. All right, so determine when it's being dilated from the y-axis. So the question is basically say what would be the dilation from the y-axis. Now when the y-axis is being dilated, it's our x values that have changed. So I've got y is equal to the root of x, and y is equal to the square root of 4x. So I now need to compare those. Yes, so this is y dashed and this is x dashed. And what do I notice? Well, I notice that this here and this here are exactly the same. And so I know that x must be equal to 4x dashed, and I know that y is equal to y dashed. So we know that the original graph had coordinates x, y, and we know that the image became x dash y dash. So do you remember previously when we had our example when we were trying to equate, we ended up with getting x and y on its own so that we could substitute it into the equation. We now need to do it backwards. So rather than getting x and y on its own, we want to get x dashed and y dashed on its own. How are we going to do that? Well, we've got two equations here. We now know that x dashed is equal to x on 4, and we know that y dashed is equal to y. Well, that's fairly obvious. So I can now say that x comma y has become, or x dashed is now x on 4, and y dashed is equal to y. And lo and behold, ladies and gentlemen, I now know that to be able to go from y is equal to the square root of x to y is equal to the square root of 4x, I need to dilate 1/4 away from the y-axis. Yeah, so dilate by a factor of 1/4 away from the y-axis. So now continuing, let's do the same with the x-axis. So once again, we had y is equal to the root of 4x. And y is equal to the root of x. Now, when we're dilating away from the x-axis, it's the y value that's changing. So what I'm actually going to do is I'm going to rearrange this. So I'm going to say that y dashed is equal to the root of 4 times the root of x dashed. Now, we know what the root of 4 is. It's 2. So that's y dashed on 2 is equal to the root of x dashed. Now, why is that important to me? Because it's the y values that's changing. And when I compare this to y is equal to the root of x, then what we see is that y has become equal to y dashed on 2, and x is the same as x dashed, just by comparing those two. And the great thing here is to change the equations around to help you to do that. We're doing it backwards, so I don't want x and y equals, I want x dashed and y dashed equals. So again, I know that x dashed is equal to x, and y dashed here would be equal to 2y. And so I've gone from x, y to my image of x dashed, y dashed. We now know that x dashed, y dashed is the same as x, comma 2y. And as such, I can now compare those two and know that what I've done is I have dilated by a factor of 2 from the x-axis. Now again, this stuff is freaking awesome, and the more you practice, the better you get. All right, doing it backwards, I've seen the requirement to be able to do that. I've certainly seen things in exams that require you to use this type of dilation, transformations, whatever. Sometimes using shortcuts is simpler, sometimes using the algebra is simpler. But this is video 2. We're going to move on in a moment to reflections, which is freaking awesome. And so think about your reflection. But otherwise, I'm going to call it a day. Thank you so much once again for joining me. And if you would be so kind as to send Fly Killer over here, because I have a very persistent Fly who obviously wants to get in on the action, probably knows maths better than I do. And anyway, thank you very much for watching. If you would do me the honor of subscribing, that would be greatly appreciated. Wow, 2 flies. Otherwise, I look forward to seeing you next time. There is a subscribe button for you to hit if you would. Otherwise, there is a video loading for you over there. Thank you so much. Been good to see you. I look forward to seeing you next time. MaffsGuru out.